polymorphisms. Now, the mode of inheritance of drug variation given to the patient follows the same general rule in biology, so that we can have the monogenic inheritance and polygenic unimodal. This monogenic or Mendelian fashion can be autosomal or sex-linked. The autosomal can be dominant, like in hepatic porphyrias, or recessive in slow acetylation of isoniazid. And the other one is a sex-linked, which can be dominant or recessive. Now, the pharmacogenetic disorder can be classified. This is an example of the classification in which we have less enzyme or defective protein. We have a classical example here, succinylcholine apnea, and then acetylation polymorphisms. And then an increased susceptibility to drug-induced hemolysis, like glucose 6-phosphate dehydrogenase deficiency and other hemoglobinopathies, and the CYP monooxygenase polymorphisms. The first example of this is succinylcholine apnea. The succinylcholine is a substance, is a drug that is used for neuromuscular blocking agents. This drug is used to have a relaxation of the striated muscle during general anesthesia. This drug is metabolized by butyrylcholine esterase. Now, enzyme defect of the butyrylcholine esterase may result in increased apnea or prolonged apnea, or it may cause a succinylcholine resistance. In common population, the administration of succinylcholine will induce apnea as long as 3 to 6 minutes, period. In heterozygote individuals, UA, we have 5 to 12 minutes apnea, whereas in homozygous AA, we have 50 to 65 minutes apnea. So this succinylcholine apnea is shows us a very dramatic effect of a drug which clinical effect is evident by variation in genetic aspects. It has been studied, the butyrylcholine esterase or succinylcholine apnea at the molecular level. So what we can see here, there is a mutation at codon 70. In UU, we have DNA sequences as normal, whereas in heterozygote or homozygote, we have aspartic acid at number 70 is converted to glycine at nucleotide 209, in which we see the codon G80 is converted to GGT. This slide shows us the role of reduced glutathione, or GSH, in maintaining a normal red blood cell membrane integrity. Along its life, a red blood cell protein is subject to oxidation by various oxidants. A normal red blood cell protein must be protected from oxidation, which is conducted by reduced glutathione, so that it remains flexible and can easily enter small capillary blood vessels. By neutralizing the oxidant, the reduced glutathione, or GSH, is oxidized to become the oxidized form, or GSSG. Now, since the red blood cell is exposed throughout its life to oxidants, the reduced glutathione, which has been oxidized, must be recycled. And this is done by G6PD. As shown here, the biochemical pathway is the conversion of G6P to G6PD catalyzed by G6P dehydrogenase. And this pathway is coupled with the conversion of NADP to NADPH. The resultant NADPH then serves as a hydrogen donor to reduce the oxidized glutathione, GSHG, back to the reduced glutathione, or GSH. In patients with G6PD deficiency, there will be less NADPH produced, and this will result in less reduced glutathione produced from GSHG. The red blood cell membrane, which contains more oxidative protein, becomes rigid and can easily break up, which we see as an hemolysis. Example of the drugs are acetanilate, methylene blue, nalidixic acid, that is the urinary tract infection drug, naphthalene, nitrofurantoin, and then anti-malarial drugs like pamaquine, pentaquine, and then sulfonamide like sulfacetamide, and so on. Okay, thank you very much for your kind attention. Now we have finished with the lecture or discussion on pharmacodynamics and pharmacokinetics. I hope you have questions, maybe a lot of questions, and you may address to me either come to my department